Okay, welcome back everyone. Thank you for coming. So this is the second lecture on three-term arithmetic progressions, the slice rank polynomial method and the Erdös-Ginzburg-Ziv problem. Does the sound work properly? Can you hear it? Great. Okay, so as announced last time, today we'll actually discuss sort of how the slice rank polynomial method works. But let's start with some quick reminders from last week. So throughout today, P will be a fixed prime, at least 3, and N will be large. So P is given, and N we should think of as much larger than P. And so then we discussed last week that a three-term arithmetic progression Fp to the n consists of 3 distinct vectors x, y, z, so that x plus z equals to y, so y is exactly in the middle of x and z. So they satisfy this equation. And so the question that we already discussed last week was, if you're supposed to find a subset of Fp to the n without a three-term arithmetic progression, how big can you make this subset? So what's the maximum possible size of a subset in Fp to the n without a three-term arithmetic progression? So that's the question, and in order to talk about what's known about this, we need some notation. So the notation we already used last week was we denote the answer by R3 of Fp to the n. Okay, so we discussed this last time. We also discussed R3 of n, which is sort of the integer analog. So this is the finite field analog of the even more classical question of R3 of n. But today we are focused on the finite field case. And so we also already discussed last week that Ellenberg and Gijswijt, so there's sort of, I guess, a history of work on these problems. But then depending on how you count, 8 or 9 years ago, so the preprint appeared in 2016, Ellenberg and Gijswijt made a big breakthrough on this question, on bounding this quantity. So they proved that for any fixed prime p, at least 3, we have that R3 of Fp to the n is at most Cp times p to the n for some constant Cp strictly less than 1. And importantly, this constant Cp is only allowed to depend on p and not on n. So in other words, they showed that this R3 of Fp to the n is exponentially smaller than p to the n. So in other words, if you're sort of choosing a subset of Fp to the n without a three-term arithmetic progression, then that subset needs to be exponentially smaller than the ground set size p to the n. Okay, so the proof of Ellenberg and Gijswijt, and we'll see sort of not the original proof, but a proof of this statement shortly. So their proof gives that the following value for Cp, which is given by this sort of minimization. Maybe just a few remarks about this. I mean, it's not terribly important, but just a few remarks. So a priori, I guess it's maybe not even obvious that this minimum is well defined, right? Because I wrote minimum and not infimum. But you can see this as follows. As t approaches 0, this approaches infinity. And so as t approaches 1, this approaches 1 over this approaches 1, right? Because if you plug in t equals 1 here, then you get p divided by p, so you get 1. But you can also check that the derivative of this function at t equals 1 is positive, and so that means then by compactness arguments that there must be a minimum attained inside this open interval, and that minimum is strictly less than 1. So indeed, the Cp is strictly less than 1. Okay, so what's maybe, so that formally shows that Cp, so that this is well defined and is strictly less than 1, but more interestingly, how big is it actually? So we also discussed that last time. It's between 0.84 and 0.92, and as p grows, it approaches 0.841 and so on. So you can think of this Cp to be roughly 0.85, or if p equals 3, maybe more like 0.9. Okay. So that's the upper bound of Ellenberg and Gijswijt. Just sort of for completeness, let me briefly mention the lower bounds. We discussed that last week already, and we won't talk more about this today. But just to, so it's not, so we have this very nice upper bound, but we don't know whether that's tight. We don't know whether that's the answer. The best known lower bound for reasonably large p is this result we discussed last week. Of Christian Elsholtz, Zach Hunter, Laura Posk, and myself. where we showed that R3 of fp to the n is at least 0.54 p to the n if n is large with respect to p, and then for small p, some better bounds are known specifically for p equals 3, this bound of 2.2202 to the n, n minus little o of n is known by Romera, Paredes et al. Using artificial intelligence techniques, and then for p equals 5, that's 3.271 to the n minus little o of n is the best known lower bound due to Essol's, Lipnik, and Siebenhofer. Yeah, so that's just as a reminder for lower bounds, but today we focus on the upper bound. Okay, so this proof of Ellenberg and Gijswijt, I briefly mentioned this, but I didn't write it down, so I wrote it here now. So this proof of Ellenberg and Gijswijt used a completely different method than the previous works on this problem. Namely, it used a new polynomial method. Like polynomial methods in combinatorics had been sort of used for several decades before, but they used a new type of polynomial method. And this new polynomial method was introduced actually not by them, but by Courtleff and Prach just a few days before this work of Ellenberg and Gijswijt came out. So Courtleff and Prach introduced this new polynomial method for a similar problem in Z modulo 4 to the n. And so then Ellenberg and Gijswijt noticed that you can sort of look at this a little bit differently and then also apply it for fp to the n. And so things happened very quickly. Then again, within the space of a few days or maybe 1 or 2 weeks, Tau then reformulated the proof of Ellenberg and Gijswijt in a way that also generalized this new polynomial method. And this sort of more general form is now called the slice rank polynomial method. And so that's the middle part of this title. And so most of today's lecture is focused on sort of explaining how this method works and showing some applications. Okay, so in particular, the next thing we do is we'll discuss the proof of this theorem, but not Ellenberg and Gijswijt's original proof, but this reformulated proof of Tau with the slice rank polynomial method. And so, yeah, let me just mention that the method since then has also had several more applications, and we will see, well, depending on time, we'll see some more later today. Okay, so so before we sort of dive into the details of this proof, we first need a bit of setup. So we first need to explain the relevant concepts for the slice rank polynomial method. Okay, so the slice rank polynomial method talks about tensors over some field. So a k-dimensional tensor, but that's nothing complicated. It's the word sounds maybe more complicated than it is. So a k-dimensional tensor over a field f is simply a function f from x to the k to f, where x is some finite index set. Okay, so what does that mean? We simply, so k is the dimension, x you should think of some usually relatively large index set, and then f are in the field f, that's where the values are. So maybe the easiest thing to think about is the case where k is 2, then this is a function from x squared to some field f, so that's nothing else than an x by x matrix. So it's nothing else than a matrix with the rows and columns indexed by x. Maybe let's write that down. For k equals 2, this corresponds to a matrix over f with rows and columns. Yeah, so it's so for k equals 2, this is just simply a matrix where the rows and columns are indexed by the set x. So if you think of x as being the set of the integers from 1 to m, then that's just an m by m matrix. And so now if k is larger, you can still think of this in similar terms, but then rather than sort of a matrix which sort of is, I guess, fits on a piece of paper, you think of some sort of hypercube with numbers in it. So you can think of it as a hypercube with numbers or field elements in it in some grid-like way, and sort of the directions of the hypercube are indexed by x. Okay, so this notion of tensors existed long before, and there also were previously existing notions of rank for such tensors, but Tao defined a new notion of how to define a rank of such a tensor, and this rank is called slice rank. Okay, so let's define this, and maybe I actually have to write that on the next board because the definition is a bit long. So this is a definition of tau from 2016, so shortly after this preprint of Ellenberg and Gijswijt appeared. So he defined for k at least 2, a k-dimensional tensor f from xk to some field f. Okay, so we want to define what the slice rank is, but first we define what it means to have slice rank 1. So we say this has slice rank 1 if and only if for some index the tensor can be factored in the following way, that f of x1 to xk can be factored into a first factor, which is a function of just xi, times the second factor, which is a function of the remaining variables. And so we want this to be valid for all x1 to xk and x. And this should be for some non-zero functions. Okay, so we say the tensor has slice rank 1 if we can, so remember the tensor is a function in k variables, and we say it has slice rank 1 if we can factor it as a function of just one of the variables times the function of the other k minus 1 variables. And so the index for the one variable is index I. You can choose it in whichever way you want. So if for some index you find such a factorization, then you say it has slice rank 1, and otherwise it doesn't have slice rank 1. Okay, so this defines what it means for a k-dimensional tensor to have slice rank 1. So maybe to describe it in words intuitively, it means it can be factored as a function of one variable times a function of the other variables. And so now we need to, in general, define the slice rank. And so we can define that the slice rank, and that's the usual setup for these rank-like notions. So the slice rank of any k-dimensional tensor f from xk to f is the minimum number r such that f can be written as a sum of r tensors of slice rank 1. So in general, we define the slice rank as the minimum number of summands we need in order to represent f as a sum of tensors which each have slice rank 1, so which each have this factorization property. So so maybe a priori this definition looks a bit funny, but if you think about the case k equals 2, this actually precisely recovers the normal notion of matrix rank that we're all used to. So that's maybe not how one would define the matrix rank if one teaches a sort of introductory linear algebra class, but it's equivalent to the normal notion of matrix rank. And the reason for that is just that a matrix has rank 1, so a matrix whose entries are sort of f of xy has rank 1 if and only if sort of you can write the entry f of xy as some function of x times some function of y. And then the second sentence is also true, that the rank of a matrix is the same as the minimum number of summands you need in order to represent the matrix's sum of rank 1 matrices. So you can check that, really. If you plug in k equals 2, this recovers the normal notion of matrix rank. So maybe let's make that as a remark. So for k equals 2, this agrees the normal matrix rank. And maybe also to comment on these previously existing notions of rank for tensors. So in the sort of ordinary notion of rank of a tensor, which sort of existed long before and is still widely used in many other places, there, for a rank 1 tensor, you demand that the tensor can be factored as a product of k functions which each only depend on one variable. So that's a more strict condition. So this is a looser condition, so more tensors have slice rank 1 than have rank 1. And then the second part of the definition of the ordinary rank is again the same, that you talk about the minimum number of rank 1 summands. So really the new thing that Tao did here was to come up with this sort of property of factorizing into a function of one variable times a function jointly of all the other variables. Okay, so any questions about this so far? No? That's good. Okay, so maybe because the definition is a little bit clumsy, and we'll mostly today need the case of k equals 3, let me just sort of, to be very explicit, rewrite sort of this part of the definition for k equals 3. So for k equals 3, a tensor so for k equals 3, a tensor has slice rank 1 if and only if it can be factored So for k equals 3, we have 3 variables, so let me call them x, y, z. So if it can be factored as f of x, y, z is g of x times h of y, z, or as f of x, y, z is g of y times h of x, z, or as f of x, y, z is g of z times h of xy. So if one of these 3 possible factorizations exist, let's say for non-zero gh, like if g and h are 0, actually the whole tensor is 0, and so the slice rank is 0. That's why if you want to say a slice rank 1, if and only if, you have to be careful to say non-zero gh. Yeah, but so if we have such a factorization of one of those 3 types, then this tensor has slice rank 1 if the functions are non-zero, otherwise the slice rank 0. So as soon as we have such a factorization, the tensor has slice rank at most 1. And so that's what we use today, I guess, and I wanted to rewrite it in this sort of maybe slightly more clear way than this for just 3 variables. Okay, so so let's start with some easy observations. So the first easy observation about slice rank is, and maybe that's motivated by the fact if you think back for matrix rank, so the rank of an x by x matrix is always at most x, and the same is true for slice rank. So the slice rank of such a tensor is always at most the size of x. So the slice rank of such a tensor is always at most the size of x. And the reason for that is actually the reason I think that Tau called the slice rank, namely, so the reason that the slice rank is always at most x is that we can find the representation as a sum of slice rank 1 tensors just by slicing up the tensor in some coordinate direction. So if you think of sort of, say, a 3-dimensional hypercube, you can take sort of horizontal slices, where by that I mean sort of you split it in a sum of tensors, each of which is non-zero only on one of the horizontal layers and 0 everywhere else. And then you can check easily that you have such a factorization. So each of those slices, which sort of just in one horizontal layer is non-zero, is of this form. And so where you can take G to be the indicator function of the sort of which layer you're in. And so by slicing it up into these slices, you find a representation into as many tensors as the size of x, which each have slice rank 1. So that means the slice rank is at most the size of x. Yeah, is that clear? Yeah. Okay. So so let's think back to matrices. So that's also similar to matrices. And now what's another thing we all know about matrices? If you have a diagonal matrix with non-zero entries on the diagonal, then it has full rank. And the same is also true here. So for diagonal tensors with non-zero elements on the entries on the diagonal, the slice rank is equal to the size of x. And so that is a lemma that was proved by Tau. So he showed, so if k is at least 2, and let f be a k-dimensional tensor, over some field. And so now we suppose that the tensor is diagonal. So what does that mean? So suppose that if we go along the main diagonal, so if you think of a 3-dimensional hypercube, this sort of the one main diagonal from one corner to the exact opposite corner, on that main diagonal you have all entries non-zero. So in other words, you have f of x1 to xk is non-zero for all x1 to xk in x which are on the main diagonal, so which have that x1 equals and so on equals xk. So if you're along the main diagonal where the indices are all equal, then the entries are non-zero, but everywhere outside that main diagonal, all entries are 0. So suppose that this holds, but everywhere outside the main diagonal, so everywhere where x1 to xk are not all 0, we have a 0 entry. Okay, so we suppose that when x1 to xk are not all equal, so whenever we are outside the main diagonal, the entry is 0. Then, sort of that means the tensor is of a diagonal form, and so what the lemma says that it has full slice rank. So the lemma says if we are of this diagonal form, then the slice rank of the tensor f is equal to x, to the size of x. So here we know it's always at most the size of x, so the point is we have a lower bound, so we know it's actually equal to x if we're on this in the special diagonal form, like with matrices. Okay, so the proof of this lemma is, as you can maybe imagine, a linear algebraic argument. And so for time reasons, maybe I won't cover the proof, but you can believe me, it's in some sense it's just linear algebra. And it's the type of linear algebra proof with a lot of indices that if you write it to the board, somehow it's one of those proofs where you don't really feel like you get any insight from following it on the board. So for time reasons, because I'd rather show you another application of the slice rank polynomial method, let's skip the details of this proof, but you can, for example, find it. So this was actually posted in a blog post of Tao, and so there he gives a proof, and there are also some other ways to prove it. Okay, so basically what this lemma tells us is that we get a lower bound for the slice rank of f, namely that the slice rank is actually equal to x if the tensor is of the special diagonal form with non-zero entries on the diagonal. And just sort of a few more remarks. In fact, it's quite difficult if the tensor isn't sort of a very special form to get lower bounds for its slice rank. And so there are some slightly more general lemmas which sort of generalize those lemmas to slightly more general classes of tensors. But for most tensors, it's sort of not clear how you would sort of lower bound the slice rank. And that's one of the challenges when applying the slice rank polynomial method. So basically, almost all applications actually go through this lemma because basically, roughly, this is the only type of tensor where you can get a lower bound. And the slightly more general form of the lemma is actually quite complicated and therefore difficult to apply. But most applications actually use plainly this lemma. Okay, so yeah, so now, unless there are any questions? No questions? Okay, so then let's now see the slice rank polynomial method in action. So let me first give you sort of a little bit of a, well, I don't know, a spoiler or a sort of a preview how it's going to work, and then we'll go through the details of proving this result of Ellenberg and Gijswijt, which is actually not on the board anymore. But so the sort of the rough pattern when applying the slice rank polynomial method to some problem is, from the problem you're sort of given some structure, for example, a subset of fp to the n without a three-term arithmetic progression, and then using that structure, you define some tensor. And the tensor is defined by some smartly chosen polynomial expression, right? It's a polynomial method, so there the polynomial comes in. You define your tensor with some very cleverly chosen polynomial expression. And so then, hopefully, you did this in a way that you can then sort of apply a lemma like this so that you know what the slice rank is, or at least you know a lower bound for the slice rank. So in most applications, your tensor is going to be diagonal. And so then you have this lower bound for the slice rank from this lemma. And so then the second part of the proof is to upper bound the slice rank of the tensor you defined. And that's where you use the polynomial. So you defined the tensor with some polynomial expression. And so then analyzing and rewriting this polynomial expression, you want to get an upper bound for the slice rank of the tensor. And then combining this lower bound with that upper bound, you hopefully get the conclusion you want. So that's the rough pattern, but maybe it's much more clear to actually see it in action. So we will now prove this Ellenberg-Gijswijt upper bound for R3 of fp to the n with this proof following tau using the slice rank polynomial method. Okay, so we want to prove this upper bound for R3 of fp to the n following tau/polynomial method argument. Okay, so since the theorem is already erased, let's remind ourselves of the setup. So p at least 3 is a fixed prime. And we want to bound R3 of fp to the n, so that means we want to upper bound the maximum possible size of a subset of fp to the n without a three-term progression. So that means we start with any subset x of fp to the n without a three-term arithmetic progression, and then we want to upper bound the size of x. Okay, so we assume x doesn't have a three-term arithmetic progression in it, and the goal is to upper bound the size of x. So before we define our tensor, we start with a little observation. So we observe that for any x, y, z in x, we have that x minus 2y plus z is the zero vector if and only if x equals y equals z. So what's that? If x and y and z are all equal, then clearly this is 0. If they're not all equal, then I claim that x minus 2y plus z is not 0. Well, if x, y, and z are distinct, they don't form a three-term progression because we assume that x doesn't contain three-term progressions. And therefore, we can't have x minus 2y plus z equals 0, otherwise they would form a three-term progression. So now the last case is if 2 of x and y agree and the third is different, so for example x equals y but z is different, then you can check that this equation also doesn't hold. Because if x and y agree and this equation holds, then z also has to agree with them. So indeed, using that x doesn't have any three-term arithmetic progressions, we showed that this equation holds for vectors x, y, z in x if and only if they're all equal. Okay, so now we can use this observation to define our three-dimensional tensor. So now we define, so the reason it's a three-dimensional tensor is because we sort of argue about three variables here. So we define a three-dimensional tensor f indexed by the set x with values in fp. So our field is fp, maybe that's not surprising because it's the field we are over. The index set is x, maybe that's, so the index set is this subset here. So that's the index set of our tensor. Maybe that's also not surprising because I set up the notation like that and that wasn't a coincidence. Yeah, so we call the tensor f, and so now how do we define it? So we define it by f of x, y, z. So that means whenever we pick vectors x, y, z in x, we need to define this, and this should be some element of fp. So how do we define this? We take the product over all coordinates, right? In fp to the n, we have these n coordinates. So we take the product over j from 1 to n. And then for every coordinate, we take the jth entry of x minus 2 times the jth entry of y plus the jth entry of z to the p minus 1 minus 1. So what do I mean by this? Let me maybe write this in order to not be confusing. So x1 to xn here with these square brackets denote the coordinates of x in x, which is in a vector in fp to the n. So this any x in x is a vector in fp to the n, so it has these sort of well-defined coordinates. And the reason to use the square bracket notation rather than the more common index notation is that we already had that notation here, and that would be quite confusing if here with a lower index, I mean a vector, and there I mean the coordinate of that vector. So therefore, I decided to keep the notation more consistent throughout the whole thing to always denote the coordinates with square brackets, even though that's maybe not standard, but I think it causes less notation confusion with the other notation there. Okay, so that means this here in the inner parentheses is the jth coordinate of this vector x minus 2 y plus z. And then that jth coordinate we take to the p minus first power, subtract 1, and multiply over all coordinates j from 1 to n. So that's the definition of our tensor. That defines the value f of x, y, z, which is now indeed an element of fp. Okay, so a priori this expression, well, I mean, it came sort of out of nowhere, and that's sort of the magic that you have to choose this expression sort of very cleverly that everything works out. But we see in a moment why this is indeed a clever choice that Tao made there. So why indeed this choice is good and it has some very good properties. So the first thing we want to, maybe are there any questions about the definition? No? Okay. Okay, so then the first thing we want to check is that this is indeed a diagonal tensor so that we can apply this lemma. So let's check that it has those properties. So in other words, that whenever we plug in x equals y equals z, we get something non-zero, but whenever we plug in x, y, z, which are not all equal, we get something zero. So let's check that. So for x equals y equals z, we have, that's easy to check, that f of x, y, z. Well, if x equals y equals z, this inner parenthesis is always 0. So here we just get a factor of -1 for every j, so we get -1 to the n, which is non-zero in fp. So that's good. So indeed, for x equals y equals z, we get a non-zero value. Now, on the other hand, for x, y, z in x not all equal, we remind ourselves of this observation we made here. So if x, y, z are not all equal, then we know that this vector x minus 2y plus z is non-zero. But if this vector x minus 2y plus z is non-zero, there must be a coordinate of the vector which observes that it's non-zero. So that means, so there is some coordinate j from 1 to n, so that the jth coordinate of this is non-zero. So that xj minus 2yj plus zj is non-zero. So this is now a non-zero element in fp. If we take a non-zero element in fp and we take it to the p minus first power, we always get 1. So that's Fermat's little theorem. If you take a non-zero element of fp, then the p minus first power is going to be 1. So this means that here we get that xj minus 2yj plus zj to the p minus first power is 1, and so that means that this factor where we subtract 1 is a 0 factor. So we get a 0 factor in this product, and so that means that f of x, y, z is 0. Right? Because the jth factor of this product makes it 0. So that means if x, y, z are not all equal, we indeed have value 0. So indeed, outside the main diagonal, the tensor is 0. And here we said on the main diagonal, the values are all non-zero. So we can apply this lemma of tau, and we know that the slice rank of this tensor is equal to the size of x. So thus, f von x3 to fp is a diagonal tensor. And by Tau's lemma, so this lemma here, it has size rank equal to the size of x. Okay, so that gives us in particular a lower bound for the slice rank. And so now comes the second part. I guess I already gave a sort of preview or spoiler before. Now comes the second part where we need to upper bound the slice rank of this tensor f defined here. And in order to upper bound it, we'll use sort of the polynomial structure of this expression defining it. So on the other hand, note that f of x, y, z is a polynomial, so we define it by some polynomial expression. So now the first question, what is the degree of the polynomial? Well, if you look at this, you have n factors of degree p minus 1 each, so the total degree is p minus 1 times n. So it's a polynomial of degree p minus 1 times n. And in the variables, let's just be clear what variables we have here in the variables. So first, there are the variables which are the entries of x. So there's x1 to xn. And then there are the entries of y. And then there are the entries of z. So in total, we have 3 n variables here. We have first this group of n variables belonging to x, then the second group of n variables belonging to y, and then this third group of variables belonging to z. And in total, the degree of the polynomial is p minus 1 times n. But if we look at any individual one of those 3 n variables, the degree is at most p minus 1. And it's degree at each individual variable is at most p minus 1. Okay, so that means sort of whenever we sort of imagine multiplying out the polynomial, rewriting it as a sum of monomials, all the exponents of all the variables will always be at most p minus 1. And the total degree is at most p minus 1 times n. So every monomial in the representation has degree at most p minus 1 times n. Okay, so indeed, you maybe wouldn't want to do this in practice to multiply this product out and write it as a sum of monomials. That sounds rather unpleasant to sort of really do this on paper in practice. And we're not going to do this, but we know that in theory we could. So in theory we could multiply it out. So we know that this polynomial can be multiplied out and then written as a sum of monomials. And so we just abstractly analyze that structure without actually carrying out the multiplication. So multiplying out, we can write f of x, y, z as the sum of monomials. And so again, each of those monomials has degree at most p minus 1 times n. And in every variable, the degree, so every exponent in every variable is at most p minus 1. Okay, so maybe, yeah, let's write at least the first part. So each monomial has degree at most p minus 1 times n. And so given that the degree of the monomial is at most p minus 1 times n, we can look at the contribution of this degree at most p minus 1 times n, coming from the x variables, or the y variables, and the z variables. And in total, the sort of degrees in the x variables, the degree contribution of the x variables plus the degree contribution of the y variables plus the degree contribution of the z variables is in total at most p minus 1 times n. So we add up 3 numbers whose sum is at most p minus 1 times n. So that means at least one of the 3 numbers must be at most p minus 1 n thirds. Otherwise, the sum is too big. So therefore, its degree in the x part is at most p minus 1 n thirds, or its degree in the y part is at most p minus 1 times n thirds, or its degree in the z part is at most p minus 1 times n thirds. So we can sort of split the monomials into three groups, where in the first group the x degree is at most p minus 1 times n thirds, in the second group the y degree is at most p minus 1 times n thirds, in the third group the z degree is at most p minus 1 n thirds. Okay, and so that means, in other words, we can write each of those monomials in one of the following forms. So each monomial occurring in the representation of f of x, y, z, each monomial is of one of the following forms. So either it's of the, well, not either, but it's of at least one of the three following forms. One form is x1 to the d1 times x2 to the d2 times and so on times xn to the dn times some monomial in the remaining variables, so y and z. Or it's of the same form with the roles of x, y, and z interchanged. So here this just sends some monomial function of the y's and the z's, I mean, of those variables. Or of the form but so very importantly, so now comes really the important thing. So far that's sort of just very generic, but the important thing is that these d's in total are not too big. So these d's, first it's important that individually they are at most p minus 1. So that's because we already said that every variable appears everywhere with degree at most p minus 1 times n. So these occurring exponents, di, are all at most p minus 1. And so then the second important thing is that the sum of d1 to dn is at most p minus 1 times n third. So that was exactly what we said here. Every monomial has has at least one of the following three properties, namely the x degrees are at most p minus 1 times n thirds, or the y degrees are at most p minus 1 times n thirds, or the z degrees are at most p minus 1 times n thirds. And so that's exactly what this says. So in the first groups, the first type, the x degrees are total at most p minus 1 m thirds, and the second thing for the y, and the third thing for the z. So that means really this analysis tells us that every monomial of f of x, y, z has one of those three forms. So it may be of multiple forms, but then you decide whichever way you want for one of those forms and write it in that form. So every monomial will now be written in this form. in one of these three forms with these conditions on D. And so if you do that now, for every monomial of f of x, y, z, writing it in one of those forms, then you'll see that you always have this first factor and then some second factor. And some of the monomials will have the same first factor, because I guess there's only these three types, and there's only a certain number of options for D1 to Dn. And so let's now put all the monomials together, where in this representation we have the same first factor. So where we're in the same of those three groups and the same tuple of D1 to Dn. So we put together the terms where this first factor is the same, and then we use the distributive law, sort of adding up the second factor. So putting together terms with the same first factor we can write f of x, y, z as a sum of terms of the form. Okay, now it's basically copy-pasting here. So it's the same, except that when we sort of add up those monomials in the second factor, then we get a polynomial. But for clarity, let me write it again. Why I raised this, keep in mind our goal was to get an upper bound for the size of x. Okay, so we put together terms here which are the same first factor, and then use the distributive law on the second factor. And so then we, in the resulting representation, we have terms of the form x1 to the d1 and so on times xn to the dn times some polynomial of y1 to yn z1 to zn or y1 to the d1 yn to the dn times some polynomial x1 to xn. And then the third type is again the same as z here in the first factor. Okay, so we get terms of this form with again the same constraints in D. So again with d1 and so on to dn and 0 and so on to p minus 1 to the n, so that their sum d1 plus and so on plus dn is at most p minus 1 times n over 3. Okay, so we have now written f of x, y, z as a sum of terms of this form and this form and this form, and each of those terms has these d's satisfying those constraints. And so for every possible sort of n tuple of d's, so for each of such tuples with these constraints, there's only one term of this form, one term of this form, and one term of this form, because if they're multiple, we sort of again put them together. So that means we have now represented f of x, y, z as a sum of nice terms. And so why are they nice? Well, each of those terms you can now see is a slice rank 1 tensor. Because each of those terms can be factored. So let's look at the first type of term. Then it can be factored as function just depending on x times a function just depending on y and z. And similarly, for the second type, we get a factorization, the function just depending on y times a function depending on x and z. And similarly, in the last, we get the function just of z times the function of y and x. And so that means each of those terms is a slice rank 1 tensor. So that means we have written f as a sum of slice rank 1 tensors. So each of these terms is a slice rank 1 tensor. So that means we have found a representation of f as a sum of slice rank 1 tensors. And so we know that the slice rank of x, the slice rank of f, we already know was equal to x, right? We wrote that somewhere here. F has slice rank equal to x, but on the other hand, we can now upper bound the slice rank of f because we found a representation of f as a sum of slice rank 1 tensors. Maybe that's not the optimal representation. Maybe there's one with even fewer terms, but certainly the minimum number of slice rank 1 tensors required in order to get f as a sum is at most the number of terms here. And so that means we got an upper bound for the slice rank of f. So the slice rank of f is at most the number of terms in this representation. And so how many terms are there? Well, there's these 3 types. And then for every type, there's one for each of those d tuples. So the number of tuples d1 to dn in 0 and so on to p minus 1 to the n, with the property that d1 plus and so on plus dn is at most p minus 1 times n thirds. The number of such d tuples multiplied by 3 is a number of terms here, and therefore an upper bound for the slice rank of f. So that means we now got an upper bound for the size of x. And that was our goal, right? Remember, our goal was to upper bound the size of x, and we have now found an upper bound in the size of x. So now you might wonder, well, this upper bound looks sort of very complicated, and we have no clue what it is. But actually, if you just want to convince yourself that, so maybe you don't care exactly about the bound with this particular CP that Ellenberg and Gijswijt got, but if you just want to convince yourself that the bound is exponentially smaller than p to the n, then you're basically already done. Because I claim that it's easy to see with a little bit of probability theory that this bound is exponentially smaller than p to the n. And the reason is just if you take this d1 to dn to be random here, so then the total number of such tuples, d1 to dn, is p to the n. But the question is now what fraction of them satisfies this inequality? Now, if you take d1 to dn random, so they're independent random variables, each sort of in the range of the integers from 0 to p minus 1, then if you take them randomly, in expectation, the sum is p minus 1 times n over 2. So the probability that it's quite a bit smaller, namely at most p minus 1 times n over 3, is now by standard concentration estimate, so by Chernoff bounds, exponentially smaller than n. So that already shows you that this is exponentially smaller than p to the n. Okay, but if you care a bit more, we can actually also bound this. It's not very hard to bound this to actually get the term out that Ellenberg and Gijswijt got. So basically, maybe just to be clear, how to bound this was not the new stuff in Ellenberg and Gijswijt's proof or Tau's proof. Like how to bound terms of this form, people already knew before. But the crucial new insight was to get sort of that upper bound on the size of x. But yeah, just for the sake of completeness, let's also bound this now to get the bound we claimed. So I call this a fact. d1 to dn. We look at all tuples d1 to dn, where each of these di's is something from 0 to p minus 1. But you only look at those where the sum is at most p minus 1 n thirds. And you wonder how many of them there are. And this fact claims that this number is at most the minimum over t between 0 and 1 of 1 plus t plus and so on plus t to the p minus 1 divided by t to the p minus 1 thirds, and this whole thing to the n. And so that exactly then gives you the bound for CP that we had on the board earlier. Because I guess the CP we had on the board earlier had also a p factor here, but then we looked at the bound was CP times p, and that exactly cancels that additional p factor. So if we sort of get that bound, then we basically get exactly what was claimed before. So let's now check this fact. So proof. Okay, so again we use sort of a probabilistic view of this. So we take d1 to dn to be uniformly random here. So we take a random n tuple d1 to dn, where each of these di's is uniformly random in 0, 1, and so on to p minus 1, and they're all independent. And so now we're asking about the probability of satisfying this. So in order to check the fact, we need to show that the probability of satisfying this for this random choice here, that this probability is at most this, which is exactly the CP we had before. So if we can show that the probability of having this is at most this, then the total number of tuples d1 to dn satisfying this is at most p to the n times this number, so that's exactly that. Okay, so we need to show this. Okay, so indeed. So if we want to show this bound, then I guess we basically have to show that this is at most this for every t. So for every t, we want to check that this is at most that. So for every t, we have that this probability we care about here that's now the same. So remember, we fixed our t. This event, that the sum of d1 to dn is at most p minus 1 times n thirds, we can rewrite as t to the sum. So because basically we take t to the exponent of, t to something, namely either side. So t to the left-hand side and t to the right-hand side. That t to the d1 plus and so on plus dn is at least t to the p minus 1 times n third. Here the at least is not a typo, that's because t was less than 1. So because t is less than 1, this inequality exactly changes signs if we take t to the left-hand side and t to the right-hand side. So now we want to bound a probability like this. And so to do that, we can apply Markov's inequality. So because I guess these are non-negative random variables, so we can use by Markov's inequality. We can say that the probability that this random variable is at least this threshold is at most the expectation of this random variable divided by the threshold. So it's at most the expectation of t to the d1 plus and so on plus dn divided by that threshold we care about here. Okay, so now we have that bound. So now for the numerator, we are now in the very comfortable situation that d1 to dn are independent, right? Because we chose this uniformly random, so in fact these di's are independent. So this is an expectation of a product of independent random variables, so we can sort of switch the expectation and the product. So this is now the same as this, the product of these individual expectations of the t to the di. Again, the same denominator. Okay? But so now it's actually easy and we just need to plug in. Because d1 is a random variable which is 0 with probability 1 over p, 1 with probability 1 over p, and so on, to p minus 1 with probability 1 over p. So we can explicitly write down what that expectation is. So that expectation, this first expectation here is just 1 plus t plus or n plus t to the p minus 1 divided by p, and then the second factor is the same, and so on. There are n factors, so we get each of those factors is equal to that fraction, so we get that fraction to the n, and then again the same thing in the denominator. Okay, and so now we just need to rewrite this nicely to look like that. So this is now 1 plus t plus or n plus t to the p minus 1 divided by t to the p minus 1/3. Then we have this p factor, and then we take everything to the n. So this is just rewriting that, and then we get indeed that. So that means we have shown that this number of tuples that we cared about is at most this. And so now if we put everything together, so we can conclude, putting together what we got here with what we got over there, we can conclude that x, which is equal to the slice rank of f, that this is now at most 3 times that number. So 3 times the minimum of t between 0 and 1 of 1 plus t plus or n plus t to the p minus 1 divided by t to the p minus 1/3 to the n. Okay, and so this was exactly what we claimed, except of this factor of 3. So now the factor of 3 is in some sense really a lower order term here, because, I mean, the point was that this is exponentially smaller than p to the n. The 3 doesn't make a big difference, but just to make, I mean, just so that you don't worry, in fact, one can also remove this factor 3. So the bound that I claimed in the beginning is actually correct. One can remove this factor of 3 with a so-called power trick. So the factor of 3 can be removed with the so-called power trick. But for time reasons, maybe let me not go into details how the power trick works. It's a very simple trick, which is sort of basically amplifying a bound like that to then remove that extra factor. But I mean, the quality of the bound not much changes with 3, so for time reasons, we won't go through that argument. Okay, so that finishes the proof of this Ellenberg and Gijswijt bound, showing that every 3-term progression-free subset x of fp to the n is at most that size, and maybe that's a good time for a 5-minute break. Okay, any questions about the proof? Okay, so then for the rest of today's lecture, I want to talk a bit about extensions and generalizations of what we just saw, and then show another application of the size rank polynomial method. So as we've just seen, the slice rank polynomial method can be used to prove this really spectacular Ellenberg-Gijswijt bound for R3 of fp to the n, which is so much drastically better than all the previous bounds. And as you saw, the proof is also not even terribly complicated. Like, I mean, we discussed the proof in, I don't know, maybe half an hour. So basically, this slice rank polynomial method, when it applies, it's really powerful. But unfortunately, the method is also rather inflexible. And so by that I mean that if you sort of take your setting and even slight changes can change the situation from the method applies wonderfully and leads to great bounds to the method doesn't apply at all anymore and leads to no bounds. And so I want to show you an example of this. So first, the positive side. So basically, as an exercise of adapting the previous proof, so by adapting the proof above, one can show the following statement. And I mean, really, it's an exercise in adapting the proof. When I taught this proof that we just saw in the class, I gave the following thing as an exercise on the homework sheet. So I call it a theorem, but once you know the method, it's really not difficult. So the theorem is as follows. Let P at least 5 be a prime. And let X be a subset of Fp to the n. That does not contain. So previously we excluded from X 3-term progressions. So we excluded solutions to the equation X minus 2y plus z. So now we exclude solutions to a different equation. So that does not contain a solution to the equation x1 plus and so on plus xp equals 0 with x1 to xp in x not all equal. Okay? So, of course, the set X will contain such solutions where x1 to xp are all equal, because if the p vectors x1 to xp are all equal, then they will satisfy this equation because we're in characteristic P. So such solutions we will definitely find in X, but the condition is apart from those solutions where x1 to xp are all equal, the set X contains no other solutions to this equation. So we exclude sort of solutions to that equation now. The variables are not all equal. And so then the conclusion is that the size of X is at most, and now we see an expression which is similar to the one we saw before, the minimum of 1 plus t plus so on plus t to the p minus 1. And now in the denominator we have t to the p minus 1 over p and that whole thing to the n. And so this looks complicated, but it's not hard to see that that's at most 4 to the n. So that minimum here is at most 4. You can see simply by plugging in t equals a half. If you plug in t equals a half, the numerator is at most 2, and the denominator you can also bound against a half. And so then you can check that this term is indeed at most 4. Okay, so that means we get a really strong bound on the size of X. The size of X is at most 4 to the n. Here, 4 is an absolute constant, not even depending on p. Right? The ground set size is p to the n. But we get a bound of 4 to the n when we exclude solutions to this equation. So that's a really strong bound. And as I mentioned, it's a straightforward application of the size rank polynomial method, sort of adapting the proof we just saw. And by the way, so I wrote here p at least 5, but if you plug in p equals 3, this is actually precisely for p equals 3, this is precisely, again, the problem of subsets of a 3 to the n without a 3-term progression, because in characteristic 3 it's the same to ask for x plus y plus z equals 0 and x minus 2y plus z equals 0. So just a sort of side remark, this really you can view as a generalization of the problem of 3-term progression-free subsets in F3 to the n. Okay, so so this is a result you can get from the slice rank polynomial method. But in contrast, if you change the setting slightly, the method completely fails. So in contrast, for the following question. The approach breaks down. Okay, so here's the question. It's very similar to this. So again, let p at least 5 be prime. And so the question is now, what is the maximum possible size of a subset x in fp to the n that does not contain a solution to the equation, now the same equation, x1 plus xp equals 0, with x1 and so on to xp and x. But the only difference is I want x1 to xp to be distinct. Okay, so just to be clear, the difference between this and this is only this not all equal versus distinct. Otherwise, it's the exact same question. And so that really looks like it shouldn't change very much. Not all equal is, distinct, that really looks like very close. And for sort of these Fourier type techniques, they usually don't see a difference between those two things. But here, it makes everything break down. So just to be sort of maybe more clear what's happening, here we are excluding solutions to this equation where x1 to xp are not all equal. There we are only excluding solutions where they're distinct. So here we are excluding slightly more solutions. And by excluding slightly more solutions, I guess we have a slightly stronger assumption. And with the slightly stronger assumption, the slice rank polynomial method applies and the world is wonderful and we get this really good bound. But here, with this only very slightly weaker assumption where we exclude slightly fewer solutions, the method completely fails and we get no bound at all. And the reason for that is that it's exactly this not all equal which leads to a diagonal tensor. So when we sort of go through the proof, adapting the proof we saw earlier today to this setting, then this not all equal enables us to apply Tau's lemma for diagonal tensors because the natural tensor we would write down associated with that equation will then be diagonal. But with the distinct, we still know that most entries outside the diagonal of the tensor will be 0, namely all entries where x1 to xp are distinct, but we don't know that everything outside the main diagonal is 0. And so we can't apply Tau's lemma, and so the method just fails because we don't have any control over lower bounding the slice rank of the relevant tensor here. And so that is really, well, in some sense quite surprising that this method is sort of so sensitive to these small details, but really it doesn't trying this approach that works perfectly here just fails completely here. And so this example is not just meant as an example of a question cooked up to show that peculiarity. In fact, this question is sort of a relevant and important question closely connected to the Erdös-Ginzburg-Ziv problem, which we won't talk about today, but which will be talked about in the 2 remaining lectures on March 3 and March 10. And so there basically, at least in high dimension, the Erdös-Ginzburg-Ziv problem basically just reduces to that question. And so it's really a shame that the method doesn't in itself apply, and then we'll see in the next 2 lectures what can be done about this and how it can be combined with additional tools to still give something for this question. Okay. Yeah. But let me not go into more detail here. Let me maybe instead mention a second limitation of the method. So this limitation came from having to get a lower bound for the slice rank of the tensor. So we need a special structure for the tensor like diagonal. Another limitation of the method comes from when we sort of write down the tensor for applying the slice rank polynomial method, we need to make sure that the degree of that polynomial defining the tensor isn't too high. Because if the degree of that polynomial gets too high, then in the end we don't get a reasonable bound, right? Because in the end we had this, so it's all erased now, but we had this sort of count of tuples d1 to the n, where sort of we had an upper bound coming from the degree constraints, and so we need to have a reasonably low degree polynomial in order to apply the method. And that's, by the way, the reason that the proof we just saw in the first part of today's lecture does not apply for sets without 4-term arithmetic progressions. So that's also a well-studied problem, and especially after these works of Ellenberg and Gijswijt and Tau's reformulation, all of that came out. A lot of people tried to extend the method to sets without four-term progressions, but nobody was able to do this. And I mean, it would be really great if someone has some idea of how to do it, but so far, and I guess it's been quite a few years now, nobody saw any way to salvage anything from that method for longer progressions. And there the problem is that the tensor you would naturally write down when you sort of start with a set without a four-term arithmetic progression, the degree is too high to get any useful bound in the end. Okay, so this was all quite negative news. So these were all things that the method can't do. Let me now put some positive news, so some things that the method can do. And so that's the following theorem, which also, again, sort of follows a very similar proof scheme as the one we saw before. So again, it's sort of an adaptation of the proof we just saw, gives the following theorem. And that theorem is called the k-colored sum-free theorem. Okay, so here's the theorem. And in fact, this theorem can be viewed as a generalization of this Ellenberg-Gijswijt result that we just saw. So let k be at least 3, and let p be a prime. And this theorem even makes sense if the prime p is 2. So this yields a non-trivial theorem even for p equals 2. And so now, okay, so the theorem is a bit technical, but I'll explain in a second what this is, how one could think about this. So let x1 upper index L and so on to xk upper index L for L ranging from 1 to capital L be a list of k tuples and fp to the n cross fp to the n cross and so on cross fp to the n. Okay, so what does this mean? So we have some list. It's indexed by L ranging from L1 to capital L. So capital L is the size of the list. And every entry of the list looks like this. So every entry is a k-tuple of vectors in fp to the n. So each of these x's is in fp to the n. And so for every entry of the list, we have a whole k-tuple. So we have an x1 and then there. So we start with first one tuple x1 to xk, where each of these xi is in fp to the n, and then yet another tuple, and so on. And so we have a whole list of capital L many such tuples. So let's remember each of those things is a vector in fp to the n. Okay, and so now comes an assumption for those. So suppose that for all L1 to Lk in 1 to L, so for any indices L1 to Lk, we have the following condition, namely that x1, L1, so that means for the tuple with index L1, we take the first vector, and then we take the tuple with index L2 and in it the second vector, plus and so on, plus then the end the Lkth tuple and in that the kth vector. That sum is 0 if and only if L1 to Lk are all equal. Okay, so how should we think about that? Well, so what this means is that each of these k tuples in our list in itself sums to the 0 vector. So for every index, we have this k tuple of vectors in fp to the n, and the k vectors in that tuple sum up to 0. But whenever, so you can think of this as sort of, let me maybe make a picture. I'm not sure how much that helps. But so we can think of this picture of this list. So first we have the first k tuple, then we have the second k tuple. and so on. And the end of the list, we have the last k tuple. And so this condition says that every row in this picture sums to 0, but taking a whole row is the only way to pick a vector in the first column and a vector in the second column and so on, and a vector in the last column, and have those k vectors sum to 0. So every row sums to 0, but there's no other way to combine something from the first column, the second column, and so on to the last column and get sum 0. So that's the assumption. And the conclusion is, well, then this list can't be too long. Well, clearly I can write such a list of length 1. I can just take any k tuple summing to 0. But I guess the conclusion of the theorem is, well, there's some limit to how long I can make my list. And that limit is, again, a term which looks like the terms we saw before. 1 plus t plus and so on, plus t to the p minus 1 divided by t to the p minus 1 over k to the n. Okay, so the conclusion is that we have this upper bound on the size of the list. And by the way, that's exponentially smaller than p to the n, again. So in other words, the list must be quite small, exponentially smaller than p to the n. So, yeah, because this, yeah, maybe I should mention this. This minimum inside here is, again, strictly less than p. You can, again, see that by plugging in t equals 1, then you get value exactly p, but then you have positive derivative at p equals 1, so this minimum is actually strictly less than p. Okay, so this statement looks, I would say, rather technical, and if you see it for the first time, you might wonder why anyone would care about a statement of that type. But let me try to convince you that's at least somewhat useful. So maybe the first argument to convince you is that this statement actually generalizes this Ellenberg and Gijswijt bound for R3 of fp to the n. So this generalizes the Ellenberg and Gijswijt So to see this, let me show you that if you already know this theorem, and by the way, the theorem follows sort of from basically the same proof as what we saw earlier today for the Ellenberg and Gijswijt bound. But let me show you that this is indeed a generalization of this Ellenberg and Gijswijt bound. So let me show you that if you know this theorem, then you get this bound for R3 of fp to the n for free. Namely, if you start with a subset of fp to the n without a three-term progression, so if this is a subset without a three-term arithmetic progression, then from that set we can construct a list of three tuples of vectors satisfying this condition. So we apply this theorem for k equals 3. So then the list of vectors. So if we list of triples of vectors. Right? If you apply the theorem for k equals 3, we need triples of vectors. Namely, we take x minus 2xx for all x and x. So for every x and x, we form a triple, and that triple is just x minus 2xx. So these are the triples in our list, and we list them below each other, like here, for all the x and x. And so now we need to check this condition, Well, the first part of the condition was that every row sums to 0. So that's certainly the case, because x minus 2x plus x, that's 0. And then the second condition was that I'm not able to pick something from the first column, the second column, and the third column and get 0. But indeed, that's exactly the same as saying that I don't have a solution to x minus 2y plus z equals 0, where x, y, and z are not all equal. So by this condition that there are no three-term arithmetic progressions, I know that if x, y, z are not all equal, then I don't have x minus 2y plus z equals 0. And therefore, I satisfy that condition here. So that means, indeed, this list of vectors list of triples of vectors satisfies this condition. Okay, sorry, the sentence didn't end yet. Then this list of vectors satisfies the condition in the theorem for k equals 3. And so that means that x, which is now my size of this list, right? If I write this list for all x and x, and the length of the list is just the size of x. And so that's now at most the term that's written there, 1 plus t plus and so on, plus t to the p minus 1 divided by t to the p minus 1/3 to the n, right? Remember now this k there is now 3. So we get that bound. So indeed, we recover this Ellenberg and Gijswijt bound for R3 of fp to the n from that theorem. Okay, so that theorem is sort of more general than the Ellenberg and Gijswijt bound. And as we discussed last week and also briefly at the beginning of today's lecture, we don't know whether the Ellenberg and Gijswijt bound is tight. But interestingly, this bound is tight. So that's a more general statement. And for that more general statement, that bound actually is known to be tight in the sense that that sort of base of that exponent is tight. So the bound in the theorem above, so that means that theorem is essentially tight in the following sense, namely there exist for any p and any k, there exist such lists of k tuples in fp to the n cross fp to the n and so on. Of size L being, well, not exactly what's written there, but the same constant in the base. So again, the same 1 plus t plus and so on plus t to the p minus 1 divided by t to the p minus 1 over k. And then in the exponent, there's an error term. So the exponent is n minus a constant depending on p and k times square root n. So that's a lower order term. And so that means that base here, that constant here that we get here is tight in this more general version of the theorem. In Ellenberg and Gijswijt's original theorem for R3 of fp to the n, as we discussed, we don't know whether it's tight. But in the more general version, it is tight. Okay, so let me also give the reference. So that's work of Laszlo Miklós Lovász, so the junior Lovász and myself from 2019 in this generality, and it was earlier proved for k equals 3 by Kleinberg, Saar, and Speyer in combination with works of Peabody and Noreen. So basically, in the case k equals 3, Kleinberg, Saar, and Speyer had a proof conditional on some conjecture which they weren't able to prove, but then Peabody and Noreen independently proved that conjecture. And so those papers together established this tightness for k equals 3, and for more general k, it's a slightly more recent result. Okay, so that's so that's this k-colored sum-free theorem. And what's interesting about it is A, that it generalizes the Ellenberg-Gijswijt bound, but B, that in this more general form the bound is tight. But there's also a C so far, so that maybe these are two good reasons to care about this already, but there's actually a third reason, and in fact, a statement of that type, at least for k equals 3, was written down as a conjecture sort of much before this Ellenberg-Gijswijt work came out, namely by Alon, Spielke, and Umans. They conjectured a statement like this for k equals 3, the reason they sort of cared about that statement is because it has implications on the so-called Erdös-Szemerédi sunflower problem, which we talk about in a moment, and also on the problem of certain approaches for fast matrix multiplication algorithms. So if you want to multiply binary matrices, the question is how fast can you do that? And that's a big question in theoretical computer science. And there were certain proposed algorithms to sort of obtain certain proposed approaches to obtain fast algorithms for this. But those approaches relied on the existence of a certain combinatorial structure, and Alon, Spielke, and Umans showed that this theorem, which back then they didn't know, but now we know it, shows that those structures don't exist. So those approaches of getting fast matrix multiplication algorithms can't work. So hopefully that gives you enough evidence that this statement, even though it looks really strange, actually is sort of justified to write down and look at, even though it looks rather technical. Okay, but so the rest of the remaining 20 minutes I want to use to tell you something about the Erdös-Szemerédi sunflower problem. Okay, so this Erdös-Szemerédi sunflower problem is a classical problem in extremal set theory. And just to avoid confusion, there's also a slightly different version of the problem called the Erdös-Rado sunflower problem, which is also a classical, maybe even more well-known problem in extremal set theory. But that we won't talk about here. So on that, there has also been spectacular work recently, but with completely different techniques. And so what's related to the slice rank polynomial method and the theorem and those things, that's just the Erdös-Szemerédi version of the problem, and so that we focus on that one. Okay, so it's a problem in extremal set theory, so that means it's sort of asking similarly to these extremal questions in additive combinatorics that we looked at so far, where we asked at how big of a subset of fp to the n or something like that can you get when excluding solutions to certain equations. It's similar here. Here it's how big of a family of subsets of some ground set can you make when excluding certain configurations. And so the configurations we want to exclude are sunflowers. So let me first define what a sunflower is. So 3 distinct sets A, B, C form a sunflower if A intersect B is the same as B intersect C is the same as C intersect A. So maybe it's easiest to understand this with a picture. So they form a sunflower if it somehow looks like this. That this is one of the sets, let's say this is A, this is one of the sets, say that's B, and this is one of the sets, say that's C. So in other words, they have a common core. Well, I mean, the core can be empty, but sort of they may have a common core, but otherwise they're disjoint. Or yet another way to say this is every element lies in either 0, 1, or 3 of the sets, but there's no element lying in just 2, but not 3 of the sets. So that's a sunflower. And if you look at this picture, maybe the first thing you would think of is not exactly a sunflower. I don't know why they came up with this name, yeah, I think the idea is that's sort of a flower with a core and then some petals around it. Okay, so here's now the problem. So that's the Erdös-Szemerédi sunflower problem. So the problem is, for given n at least 2, so that's the ground set size, what is the largest possible size of a family F of subsets of, let's say, the numbers from 1 to n. It doesn't really matter what you take as your ground set. Let's, for simplicity, just take the numbers from 1 to n as your ground set. And the question is, what's the largest possible size of a family of subsets of this ground set that does not contain three distinct sets ABC in the family forming a sunflower. Okay, so the question is, again, you start with this sort of ground set, and so now your universe are all subsets of this ground set. And from that universe, how many things can you pick? So how many subsets of that ground set can you pick under the constraint of not picking three sets forming a sunflower? So that's the question. So maybe let's just start with a trivial observation. So clearly, any such family must have size at most 2 to the n, right? Because that's the total number of subsets we can pick from the ground set. And so then this conjecture of Erdös and Szemerédi was that, in fact, you must be exponentially better than this sort of trivial bound coming just from the total number of all subsets. So in 1978, Erdös and Szemerédi conjectured that, in fact, f is at most c to the n for some absolute constant c strictly less than 2, so that you can get exponentially better than that trivial bound. And so just a historic, to sort of get the history right, so that was conjectured in 1978, and then Allon, Spielka, and Umans showed in 2013 that this follows from that theorem over there, the k-colored sum-free theorem, in the special case of k equals 3 and p equals 3. So Allon, Spielka, and Umans showed that if this holds for k equals 3 and p equals 3, then that implies the Erdös-Szemerédi conjecture, but they didn't know yet whether that k-colored sum-free theorem holds. And so that was then when this work of Ellenberg and Gijswijt came out, and then this reformulation of tau also, it was observed by several different people that the proof carries over to that statement. So that then with this Ellenberg-Gijswijt work, then this statement was established, and so then it was sort of clear that the Erdös-Szemerédi conjecture holds. But the best known bound for this conjecture was then also shortly afterwards proved by Naslund and Sauermann, who, rather than going through that theorem and that deduction, directly applied the slice rank polynomial method to this problem. So rather than sort of going the detour through the k-colored sum-free theorem, because then the deduction from there to this is a bit lossy, so then rather than going this detour, they just directly applied the slice rank polynomial method, which was very new at the time, So they applied it directly to this Erdös-Szemerédi sunflower problem. And so then they showed the bound that the size of f is at most 3 times n plus 1 times the sum over all binomial coefficients n choose k, where k ranges from 0 to n over 3. And that one can then rewrite as 3 divided by 2. I mean, this term, I guess, is if one now analyzes this, one can rewrite this as 3 to the 2/3 to n plus little o of n. And in case you wonder how big 3 divided by 2 to the 2/3 is, it's roughly 1.89. So that means, indeed, the conjecture holds with C being roughly 1.89. Okay, yeah, so just for historic accuracy, they weren't the ones proving the conjecture because then it was known via this detour, but they proved this very nice bound for the conjecture. Okay, and so I guess I have 10 minutes left. So in this 10 minutes, I want to give you a sketch of this proof of Naslund and so on, getting this bound with a slice rank polynomial method. So we see a second application of the slice rank polynomial method. And so in order to apply this method, in fact, they reduced this theorem. So again, Naslund and Sauermann reduced this theorem to the case that all members in the family F, so all sets in the family F, have the same size. So if, yeah, so let's say under the additional assumption, so it's still assumed, and for time reasons I'm not writing this out, that F doesn't have a sunflower, but under the additional assumption that all sets in F have the same size, they proved that then F has size at most 3 times the sum of binomial coefficients. And it's not hard to see that this bound implies that bound, because you can just group. So if you have any family F without a sunflower, you can sort of sort the sets in the family F by their size. There's only n plus 1 different possible sizes, namely 0, 1, 2, and so on to n. And so now you sort them by their size. And now for every subgroup, for every subfamily with sort of sets of all the same size, you apply that bound, and then you add up over the n plus 1 different groups. So really, this very easily implies that. So really what we have to show is this. Okay, so here's a proof, or rather a proof sketch for time reasons. So we start with a family F without a sunflower and all sets having the same size, and now we're going to construct a tensor. So in order to do that, we look at every set. We look at every set A and F, and from that set we form a vector. So we consider the so-called indicator vector. Indicator vector A1, A2, and so on, AN. So again, I put the entries, so the coordinates in square brackets. So that's a vector in 0, 1 to the n. So by abuse of notation, I identify the set with its indicator vector. So that's a 0, 1 vector, which has a 1 in the positions of the elements contained in A and zeros in the other positions. So AJ is 1 if J is in A, and otherwise AJ is 0. Okay, so this way we can now interpret F as a family of vectors in 0, 1 to the n. And so now let's define the relevant tensor. So define a 3-dimensional tensor F from F cross F cross F. So that's, this F is the family, this F is the name of the tensor, and the field now we just take R. So you can also take another field of characteristic 0 if you prefer Q, but let's take a field of characteristic 0. Let's just take, for example, R, and let's define the tensor by f of ABC. So if ABC are sets in the family F, then we define f of ABC as the product, again over all coordinates, j from 1 to n, of AJ plus BJ plus CJ minus 2. And this we multiply over all coordinates from 1 to n, j from 1 to n. So these things are all 0 or 1, depending on whether j is in A, B, or C or not. And so now we form this term, multiply for all j from 1 to n, then we get some real number, and that's the definition of this tensor. So since I have 5 minutes, this will be just a sketch. But so the first observation is that this tensor is diagonal. And the reason for that is if you plug in A equals B equals C, then those numbers will be either 0 plus 0 plus 0 minus 2 or 1 plus 1 plus 1 minus 2. So it will be either these factors will be either minus 2 or 1. So if A equals B equals C, here in this product we get a product of numbers which are each either minus 2 or 1, and so that product is non-zero. So that means if A equals B equals C, I either multiply 1 plus 1 plus 1 minus 2 or 0 plus 0 plus 0 minus 2. In either case, I get a non-zero result. Now, if A, B, and C are not all equal, I need to check that that product is 0. So if A and B and C are not all equal, in other words, I need to show that there's an index j which is in exactly 2 of those sets to get a 0 factor here. So why is that? If A, B, C are distinct, they don't form a sunflower, right? Because F doesn't have sunflowers in it. So that means they don't form something like this. Something like this meant that elements are in 0, 1, or 3 of the set. So if that's not true, that means I must be able to find an element j which is in exactly 2 of those sets. Or in other words, I must be able to find an element j which is in 1 of those intersections, but not in the third remaining set. So that means if A, B, C are distinct, they don't form a sunflower. Therefore, I can find a j which is containing exactly 2 of them, and then I get here 2 minus 2, which is 0. If A, B, C are not all distinct, and that's the case place we have to be careful and use that the sets are all of the same size. If A and B and C are not all distinct, but 2 are equal and the third is different, then using the fact that they're all of the same size, I can find an element which is in the 2 equal ones, but not in the third. So for example, if A equals B, but C is different, I can find an element which is in A, but not in C, because the sets were all of the same size. And here we crucially use that they're of the same size, because this wouldn't be true if A was equal to B, but C was a strictly bigger set. So here we really use that. But with this assumption, it's fine. So even if A equals B and C is different, we can find such an element which is exactly 2 and get a 0 factor here. And so therefore, we showed the tensor is diagonal. And so its slice rank is equal to the size of the family. And so now, on the other hand, we need to find an upper bound on the slice rank. And so to upper bound the slice rank, we do the exact same thing as before, except that we now have a slightly different degree and slightly different individual variable degrees. But the total degree of the polynomial is at most n. So that means either in the A group or the B group or in the C group, I have a degree at most n over 3. And then in every individual variable, the degree is at most 1. And so by a similar argument as before, one can show that the slice rank of the tensor f is at most, well, again, I write a representation and so on and so down. The terms I'm counting is the number of tuples d1 to dn, which are now in 0, 1 to the n, because every individual exponent is at most 1. And the sum of the degrees of the terms that matter is now at most n over 3. So that's again because every monomial has degree at most n, so that means the degree in the A variables is at most n over 3, or the degree in the B variables is at most n over 3, or the degree in the C variables is at most n over 3. And then the individual exponents are all either 0 or 1. And so that means if I do the exact same thing, which I don't have time to write out now, but it's really the same as before, then I get 3 times, so the factor 3 comes from the 3 different groups of whether it's the A's or the B's or the C's, which have small degree, and then it's the number of possible exponent tuples, which are 0, 1, every individual exponent, and sum at most n over 3. And so this is now, this time we don't have to do a sort of argument to sort of how to bound this. This is now more or less by definition at most, that term. So this is at most the sum of the binomial coefficients n choose k, where k ranges from 0 to n choose 3. So that's just because, well, you look at all different possible sums, and then for every sum you get n choose k possibilities of where to put the ones. And so that means the slice rank of f has this upper bound, but that was equal to the size of the family f. And so that means we now get that bound is claimed, and that implies that bound. And I think I'm exactly out of time. It's exactly noon. So thanks for coming.